Every year, the world consumes over 141 billion cubic feet of wood for housing, furniture, and a wide range of other products. But how can we meet this massive demand without putting extra pressure on natural forests? Part of the answer lies in what used to be considered waste. Today, RaWMachines explores how scrap wood is processed, recycled, and turned into brand new particle board. Let's dive in. Particleboard is more than just a substitute. It's like Earth's answer in the era of climate change. When wood waste ends up in landfills, it decomposes and releases methane, a greenhouse gas 25 times more potent than CO2 at warming the planet. But when collected and recycled, this problem is significantly mitigated. For every ton of recycled particle board, about 12 mature trees are saved from being cut down. As a result, forests remain intact, birds keep their habitats, and the flow of biodiversity endures. Beyond that, particle board offers substantial economic benefits. Compared to solid wood, it is more affordable and easier to mass produce. Consumers benefit, businesses cut costs, and the entire supply chain runs more seamlessly. It is a clear symbol of the circular economy, a system where nothing goes to waste, only resources waiting for a new purpose. Now, let's dive deep with RaWMachines into how this cycle works. The journey of a particle board doesn't begin with intact tree trunks. It starts with what seems to have lost all value: sawdust, wood shavings, scraps from furniture workshops, old wooden items, and even materials salvaged from demolition sites. Instead of being burned or sent to landfills, everything is collected at the factory to begin a brand new life cycle. Softwood is generally preferred due to its relatively uniform structure and ease of processing. Hardwood can also be reused, but it typically requires more energy to process. From the outside, it looks like nothing more than a chaotic pile of scrap, but inside the factory, it is the raw material for millions of engineered wood panels. And before that can happen, everything that isn't wood must disappear. The initial stream of raw material passes through high-capacity vibrating screens. Dirt, dust, bark, and small impurities are quickly separated from the wood. But the real danger lies in what's harder to see: nails, screws, iron staples, metal debris still trapped in old furniture, or wood salvaged from construction sites. Industrial magnets are positioned along the conveyor line to pull them out before they get a chance to move deeper into the system and damage the machinery. After cleaning, the raw material undergoes preliminary sorting. Larger pieces may be set aside for the core, while smaller, finer materials are suited for the surface layers. The scrap stream is cleaner now, but it is still far too chaotic to become a board. That is when the chippers go to work. Recovered wood comes in all shapes and sizes: long, short, thick, thin, sharp-edged, and even relatively large blocks. To create a uniform material, this chaos must be brought under control. The raw material is fed into the chipper, where a system of high-speed rotating blades continuously cuts the large pieces into smaller particles. In just a short time, the original shapes of most of the scrap virtually vanish. But grinding it down is still not enough. Directly downstream is a size control screening system. Oversized particles are fed back for regrinding. Oversized fines, excessively fine particles, are screened out, as they absorb too much glue without contributing to structural strength. Only particles that meet the standard, under 30 millimeters, sturdy enough and compact enough, move on to the drying stage. This is the step that transforms a chaotic stream of scrap wood into a controllable industrial raw material, laying the foundation for drying, resin blending, and mat formation in the subsequent stages. However, before bonding can occur, the moisture remaining in the wood must be controlled. The wood particles are fed into a rotary drum dryer, where hot air continuously blows through, while the material is constantly tumbled. The drying air temperature can fluctuate around 300 to 570 degrees Fahrenheit, causing the moisture inside each particle to rapidly evaporate. Throughout the process, sensors continuously monitor the material to bring its moisture content down to approximately 2 to 8%. Excessive moisture impairs glue adhesion, while overdrying leaves the particles brittle and prone to breakage. Upon exiting the dryer, the material stream is lighter, drier, and more stable, ready for precise screening before being blended with adhesives. Raw materials pass through a multi-deck vibrating screen system to be classified by size. Oversized pieces are sent back to the chipper, while dust and fine particles are removed from the production line. This classification creates the characteristic multi-layer structure of particleboard, with each particle type playing its appropriate role. After being classified by size, the wood particles are conveyed into the blending chamber, where preparation begins to bond them into a unified board. Inside, the adhesive is sprayed as an ultra-fine mist while the wood flow is continuously mixed. The goal is to coat the surface of millions of wood particles with just enough resin without causing them to clump together. This step is particularly critical as the final bond quality relies heavily on the uniformity of the gluing process. The two most common resins used here are urea formaldehyde and phenol formaldehyde. Urea formaldehyde is affordable, easy to use, and offers strong adhesion, acting like a diligent builder who gets the job done quickly and cost-effectively. Phenol formaldehyde, on the other hand, provides durability against water and weather, serving as a protective suit of armor for the board. Depending on the final product requirements, engineers will select the appropriate resin or blend both.
Because the resin clumps, it sometimes helps to add about half of the resin and then hand mix a little bit and then add the other half.
Beyond resin, factories may also add moisture-resistant wax, flame retardants, or fungicides. Everything is carefully proportioned, as too little glue leads to a weak bond, while too much not only increases costs but also negatively affects the board's properties. After being coated with adhesive, millions of wood particles are conveyed to the mat forming system, where they are evenly distributed into layers on a conveyor belt. The structure of the board begins to take shape right here. Larger, coarser particles are concentrated in the core to provide thickness and stability, while smaller, finer particles are spread on the outer two surfaces to ensure a smooth, easily finishable face later on. At this stage, the wood mat remains highly porous and full of air gaps. Consequently, it passes through a pre-press system, where rollers gently compress the material, expelling excess air and keeping the layers from shifting during transport. By the end of this step, an actual board does not yet exist. What we have is merely a shaped wood mat, ready to enter the extreme heat and pressure of the hot press. This is the defining moment of the entire line. The wood mat enters the hot press, where steel plates clamp down with pressure reaching up to roughly 600 pounds per square inch, while temperatures are maintained between about 138 degrees Celsius and over 220 degrees Celsius, depending on the board type and adhesive system. Within minutes, heat penetrates deep into the core, activating the binder and curing the resin. At the same time, immense pressure forces millions of wood particles tightly together, eliminating most air gaps and locking the board structure into place. The roar of metal, the heat radiating from the edges of the press, and the sharp, pungent scent of resin wafting through the air, it all creates a genuinely exhilarating atmosphere. As the press opens, the once loose layer of material has transformed into a flat, solid, structural board. This is the exact moment those pieces of wood, once written off as waste, officially begin a brand new life cycle. But the journey doesn't end there. Though the board has achieved structural integrity, its edges remain rough and short of final commercial dimensions. It is therefore routed to an automated trimming system, where saw blades trim away excess edges and unstable areas, squaring up the panel. Next, the panel is cut into standard 4 by 8 foot dimensions, common in furniture and construction applications. However, the production line can also be adjusted to yield custom sizes based on order requirements. Upon exiting the hot press, the board has achieved a solid structure, but it still retains an immense amount of heat, especially in its core. At this point, the temperature difference between the interior and the surface can be substantial, creating internal stress within the material. If cooled too rapidly or moved directly to the next stage, the board risks warping, uneven shrinkage, or even cracking and deformation. Consequently, it must undergo a stabilization phase before further processing. The panels are fed into a cooling system, where they are arranged to allow air to circulate across both surfaces. Industrial fans continuously circulate air, helping heat from the core slowly dissipate outward and escape into the environment evenly. In modern production lines, thermal sensors constantly monitor both the surface and core temperatures of the panel. Only when the temperature drops to an appropriate level and the structure reaches equilibrium is the product moved to the next step. This serves as a necessary rest period after enduring the immense heat and pressure of the hot press, allowing the panel to stabilize its shape, relieve stress, and prepare for the sanding and surface finishing processes ahead. Despite having a fully formed shape, the surface of the pressed board remains quite rough, marked by minor unevenness and wood fibers. This is where the precision sanding machine comes into play. A series of massive sandpaper-covered rollers arranged in sequence spin at high speeds. As the board is fed through, each roller glides across the surface in turn, stripping away thin layers measuring just a few hundredths of a millimeter. This process demands exceptional consistency. Sanding too much can cause the board to lose its standard dimensions, while sanding too little leaves small imperfections behind that become even more noticeable once the decorative overlay is applied. Because of this, the pressure, sanding belt speed, and amount of material removed are all strictly controlled. At the same time, a heavy-duty dust extraction system continuously collects dust and wood fibers. This keeps the production environment cleaner and prevents dust particles from settling back onto the freshly finished surface. By the time they exit the sanding machine, the once rough boards feature a smooth, flat surface and uniform thickness. From here, they are ready to be coated with melamine, laminate, paint, or other decorative layers before being transformed into tables, cabinets, shelves, and a wide variety of everyday furniture. Before becoming a finished product, every panel must pass through a rigorous quality control process. Automated cameras and sensors scan the entire surface, checking thickness, flatness, and detecting defects, such as cracks, warping, or dimensional discrepancies. Any panels that fail to meet requirements are immediately marked and routed off the line. Additionally, select samples from each batch are sent for testing to evaluate bending strength, internal bond strength, and structural stability. Only the panels that clear every standard are certified as finished goods and forwarded to the final packaging stage. The final stage of the line is packaging. Automated robots stack the panels into neat bundles, which are then wrapped in shrink film. Each pallet is labeled with a barcode and integrated into the warehouse management system, enabling fast tracking of key information such as manufacturing site, completion time, and batch specifications. However, even at this final step, environmental impact must be taken into account. Traditional plastic shrink wrap is difficult to recycle and adds pressure to waste management systems. Consequently, some factories are testing alternative packaging materials, ranging from molded fiber packaging to biodegradable films. These initiatives demonstrate that sustainability goals must extend through the entire production chain, rather than focusing solely on recycling wood waste. From loose scrap wood at the start, through numerous stages of processing and testing, the end result is a collection of flat and fixed, sturdy, uniform panels. They are stacked into large units in the warehouse before being shipped to various markets, where they will be further processed into tables, chairs, bookshelves, cabinets, or interior partitions. Thus, completion marks not only the end of the production line, but also the conclusion of a transformation from waste into useful material. What was once considered garbage now carries a new form, a new function, and a new value. That is the ultimate fulfillment in the journey of reborn wood. Another rapidly growing segment is the use of sawdust to produce wood pellets, one of the world's fastest growing renewable energy fuels. The production process begins as sawdust and wood waste are shredded to create a uniform size. Next, the dry raw material is fed into a high-capacity press and extruded through metal dies under high pressure. At this point, friction generates heat that softens the natural lignin in the wood. Lignin acts as a binder, fusing the sawdust particles into small, dense, and firm fuel pellets without requiring added chemical adhesives. Once formed, the pellets are cooled and screened before use. Thanks to their compacted structure, wood pellets feature a high energy density and burn efficiently. Compared to raw wood, they produce less smoke and ash. Furthermore, using sawdust and wood waste as raw materials reclaims what might otherwise be discarded, reducing resource waste while generating a valuable source of renewable energy. Today, the global wood pellet industry exceeds 40 million metric tons per year. As many countries seek to reduce their dependence on fossil fuels and transition to cleaner energy sources, demand for wood pellets continues to rise. From a seemingly low-value waste product, sawdust is being transformed into a practical fuel. These small pellets are poised to play an increasingly prominent role in the future of renewable energy. Another major destination for sawdust is the sawmill's biomass boiler. Instead of being discarded, sawdust and wood waste are transported by conveyor belts into giant biomass boilers, where they burn at high temperatures and release a substantial amount of heat. This heat converts water into high-pressure steam. The steam can then be used to drive turbines to generate electricity, or pipe to dry kilns to season fresh batches of lumber. What makes this process special is its nearly closed-loop cycle. Raw logs enter the mill, the high-value portions become finished products, and the remaining waste is turned into fuel to power the production process itself. In some large-scale sawmills, the volume of wood waste generated is so significant that it not only powers and heats the entire operation, but the surplus energy can also be fed back into the local power grid. Once viewed as mere waste, sawdust has now become the final link that enables sawmills to be self-sustaining. The final destination for sawdust is agriculture. Sawdust is one of the most commonly used materials for animal bedding, particularly for livestock and poultry. Thanks to its porous, lightweight texture and strong absorbency, sawdust soaks up urine, moisture, and waste, keeping the barn floor drier and cleaner. The layer of sawdust also creates a cushioned surface, preventing animals from making direct contact with cold, hard flooring. Additionally, sawdust helps minimize odors and improve barn hygiene. When combined with microbial products, sawdust can serve as deep bedding, accelerating waste decomposition, and reducing environmental pollution in farming areas. This helps create a cleaner, healthier living environment for livestock to thrive. And so, we have come to the end of a long journey, from discarded wood scraps, shavings, and sawdust that seemed completely valueless to their rebirth into entirely new forms. Through a series of steps, collecting, cleaning, shredding, drying, blending, and pressing under high heat and pressure, wood residue that might otherwise have simply been burned is transformed into strong, uniform particleboard. From there, it makes its way into the tables, cabinets, bookshelves, and everyday furniture pieces that surround us. Yet, the journey doesn't stop with particleboard. Even the smallest particles, like sawdust, continue to yield value. They are compressed into fuel pellets, fed into biomass boilers to generate heat and electricity for the mill itself, or repurposed as animal bedding in agriculture. Every waste stream finds a new destination rather than taking up space in a landfill. Looking back at the whole process, what stands out most isn't just the massive machinery or modern production lines. It's the way we are striving to extract far more value from the exact same resource. A single tree can live multiple lives. It might begin as a piece of furniture, then be recovered to become a new board. Whatever remains can go on to serve as fuel, energy, or raw material for a completely different purpose. This is precisely how a circular economy takes shape. The byproduct of one process becomes the starting point for the next. With natural resources under mounting strain, recycling does more than just divert waste. It reduces our need to extract new raw materials and extends the value of what nature has provided. Perhaps that is the deepest significance of the journey we've just witnessed. From a tiny wood scrap to a finished board, a fuel pellet, or the energy powering an entire mill, it all goes to show what we call waste isn't necessarily the end. Sometimes, it's just the beginning of a brand new life cycle. Thank you for joining me on this journey. If you found this video interesting, please don't forget to leave a like, subscribe to the channel, and share it so I can bring you even more fascinating deep dives in upcoming videos. Thank you, and see you next time.